Section 2.4 is all about postulates and diagrams. So if you remember, postulates are things that just have to be true, but they cannot be proven. And we're also going to look at diagrams, basically things that you can assume from a diagram and things that you cannot assume from a diagram. But first, let's talk about some symbols. As we've talked about before, math is just like its own language with its own words and its own symbols. In the last section, we talked about conditional statements and changing those conditional statements into if-then form. We can actually use symbols in order to illustrate that. If I have an original conditional statement, if P, then Q, so something like if an angle is a right angle, then its measure is 90 degrees, I can actually write that as P and then an arrow Q. That arrow is read as implies, so P implies Q. So an angle is a right angle would imply that its measure is 90 degrees, so P implies Q. So that, again, that arrow means implies, and it's read P implies Q. If you remember from the last section, the converse is when you flip the hypothesis and the conclusion around. So this time, if Q, then P. So we would read that as Q implies P. Next, we have the inverse. Remember, in an inverse, you negate both the hypothesis and the conclusion. So in this case, if not P, then not Q. To show that symbolically, you use this little squiggly line for the not. So I would read this as not P implies not Q. Next, we have the contrapositive. Remember, the contrapositive is like putting the converse and the inverse together. So you flip the hypothesis and the conclusion around, and you also negate both. So in words, you would write, if not Q, then not P. Symbolically, you would read that as not Q implies not P. And remember, a biconditional is when you use if and only if, and we use that a lot in definitions. If you want to write that symbolically, you actually use the double arrow. So P, if and only if, Q is how that would be read. Before we move on to the rest of the section, let's first have a little chat about some things we've talked about previously. First, postulates and axioms are rules that are accepted without proof. So again, these are things that we just know that are true just for being living, breathing human beings on this earth. Theorems, however, are rules that can be proven. We'll see a lot of this later in this chapter and in the coming chapters where we'll be given theorems and we have to prove them based on other things that we know are true, like postulates and other theorems that we've already proven. We have already talked about 4 postulates throughout chapter 1. The first postulate was the ruler postulate. Remember, this is the one that just basically said we can take a segment and line it up with a number line and see how long it is. The second postulate that we've talked about is the segment addition postulate. It basically said that if I had a segment like this and split up into 2 parts, and it said it was 2 units here and 1 unit here, that the total length of the segment was 3. So we were just adding the 2 parts together. So segment addition, meaning I'm taking the 2 segments and adding them. The third postulate was the protractor postulate, which was much like the ruler postulate. It basically just said that you can line a protractor up with an angle and measure the angle with the protractor. The fourth postulate is the angle addition postulate, which was much like the segment addition postulate. It basically just said if I have an angle split up into 2 angles, if this angle is 15 degrees and the other angle is 30 degrees, I can add those 2 smaller angles together to find the measure of the bigger angle. In this case, it would be 45 degrees. Knowing these postulates will be pivotal when we go to prove other theorems later in this chapter and in the coming chapters. So don't ever forget about these postulates: the ruler postulate, the segment addition postulate, the protractor postulate, and the angle addition postulate. Here are 7 more postulates about points, lines, and planes, and I think you'll find these to be pretty familiar. These postulates are based off of how we name and talk about points, lines, and planes. So postulate number 5. Through any 2 points, there's exactly 1 line. This is exactly what we talked about when we talked about naming a line with 2 points, how any 2 points are always collinear because I can always draw a line through them. So anytime I have 2 points, there's exactly 1 line that I can draw through them. Postulate number 6. A line contains at least 2 points. This is kind of the converse of it. If I know I have a line, then there is at least 2 points that determine that line. Postulate number 7, if two lines intersect, then their intersection is exactly 1 point. Here again, this is something we've talked about previously. We talked about if there's two lines and they intersect, they're going to exactly intersect in 1 point. Postulate number 8, through any three non-collinear points, there exists exactly one plane. This was a problem on your test where you had to fill in the blank of three non-collinear points. You name a plane with three non-collinear points. So again, postulate number 8 is just kind of putting that into words. Postulate number 9, a plane contains at least three non-collinear points. So here again, this is kind of like the converse of it. We're just flipping it around saying if I have a plane, we know there's at least three non-collinear points on it because that's what determined the plane to begin with. Postulate number 10 is kind of obvious. If 2 points lie in a plane, then the line containing them lies in the plane as well. So here again, if I have 2 points, 2 points determine a line, and those 2 points are lying in a plane. The line that is containing those 2 points, because we know that any 2 points are collinear, the line that is containing those 2 points also lies in the plane. Postulate number 11, if 2 planes intersect, then their intersection is a line. This was something we talked about as well in chapter 1. And I gave you the visual of the ceiling and the wall intersecting along the corner of the wall. Once again, all of these postulates is just everything we talked about in chapter 1 about how to name things, how things intersect, what determines a line, what determines a plane. Again, all of those things that we talked about in chapter 1, now we're just putting into words and calling them postulates. So really none of these things should be new to you at this point. So relax and know that you know what you're talking about. Let's look at some examples. Number 1, complete the statement given the postulate. So part A, postulate 9. Plane blank contains at least three non-collinear points, blank, blank, and blank. I just took the graphic from the previous slide and copy and pasted it right here for us to refer to as we're doing these problems. Postulate 9 says a plane contains at least three non-collinear points. So knowing this and referring to our diagram up here, we can then fill in the blanks. Let's just look at this diagram first. We have plane M right here and plane P, and you can see these two planes are intersecting along this line right here, line L. So if we're looking at plane P, the only 2 points that are shown on plane P are points R and S that lie on line L, which is the place where plane P intersects plane M at. So if we're going to fill in the blanks, we need a plane that has at least 3 points on it. So we have to refer to plane M. So filling in the blanks, plane M contains at least 3 non-collinear points, R and S, those 2 points that were on line L, which is shared with plane P, and also W, because that is the plane that had 3 non-collinear points on it. Problem B, postulate number 11, the intersection of plane M and P is blank. So referring to postulate 11, if 2 planes intersect, then their intersection is in a line. We kind of talked about this before. We know that plane P is intersecting plane M along this line right here, which is called line L. So we can complete the statement by just putting line L. Let's move on to example number 2. State the postulate illustrated by the diagram. For part A, I see if 3 non-collinear points A, B, and C, then those same 3 non-collinear points surrounded by a plane. This reminds me of the postulate that states that if I have 3 non-collinear points, then I have exactly 1 plane. Looking at our list of postulates, I see postulate number 8, through any 3 non-collinear points, there exists exactly 1 plane. Therefore, this diagram illustrates postulate number 8. Part B, if 2 points A and B, then those same 2 points A and B now have a line drawn through them. So this reminds me of the postulate that states if I have 2 points, then I have exactly 1 line. Now looking at our list of postulates, I see postulate number 5, through any 2 points, there exists exactly 1 line. So therefore, this diagram illustrates postulate number 5. And then part C, if 2 points lying in a plane, then we have that same plane with the 2 points lying in it, also with the line containing those 2 points in the same plane. This diagram reminds me of postulate number 10. When I look at my list here, I see if 2 points lie in a plane, so here's those 2 points, then the line containing them lies in the plane. So here's the 2 points with the line going through them. So therefore, this line is also in the plane since the points were in the plane. So this diagram illustrates postulate number 10. Next, we need to talk about what you can assume and what you cannot assume from a diagram. When you interpret a diagram, you can assume information about size or measure only if it's marked. You cannot say, well, this angle looks like a right angle, so therefore it is a right angle. You have to be told by either in your given information where it says angle ABC is 90 degrees, or it needs to be marked on the diagram that it is a right angle. So to start, on the left, these are the things you can assume from the diagram at the right here, and the list on the right are the things you can assume from the diagram on the right. So to go through these, the things you can assume. All points shown are coplanar. So as long as the points are lying in this blue area, the blue plane, I know that all of these points inside of here are coplanar. I can also assume that angle AHB and angle BHD are a linear pair. So if we identify these, we have AHB is right here, and BHD is right here. So seeing that they are forming the straight line, I can assume that they are a linear pair, meaning that they add up to 180 degrees. Basically what this tells me is I can assume lines are straight. Next, we have angle AHF and angle BHD are vertical angles. Now remember, vertical angles are formed by the same two intersecting lines and they lie opposite each other. So if I have AHF and BHD, they're formed by these two intersecting lines and they sit across from each other, so I can assume that they're vertical angles. Next, I can assume that AH, J, and D are collinear. So A, H, J, and D, they're all lying on this line and I can assume that they are collinear because they're all on that line. And finally, I can assume that line AD and line BF intersect at point H. So here's line AD and line BF, and they intersect at point H. I can assume intersection points of two lines. The things I cannot assume that points G, F, and E are collinear. So notice I'm given 3 points. I cannot assume that these 3 points are collinear unless they are all lying on a line. So when I look at the diagram, here's point G, F, and E. It may look like I could draw a straight line through all 3 points, but since there is not a line shown, I cannot assume that they all would end up on the same line. However, if I was just given 2 points, like points G and F, I do know that any 2 points are collinear, so therefore I could assume that those are collinear. But the second you throw a third point into the mix and there's not a line drawn through all 3, you cannot assume that they're collinear. So if it's 2 points, you can assume they're collinear even if there's not a line drawn. But if it's 3 points and there's not a line drawn, then you cannot assume that they are collinear. Next, we have line BF and line CE intersect. So if we look at this, we have line BF and line CE. We are not shown that these two lines are intersecting. We also cannot assume that eventually if I keep extending it this way and this one this way, that eventually they will intersect. For all we know, they might be parallel. So therefore, if they don't intersect, I cannot assume that they will eventually intersect. On the same side of that coin, if I have line BF and line CE, I cannot assume that they don't intersect. So here again, I cannot assume that these are parallel. Just because they look like they may never run into each other doesn't mean that they are indeed parallel. We have to be told that they're parallel, or we need to be told that they intersect, or shown that they intersect, but we cannot assume either. Next, I cannot assume that angle BHA is congruent to angle CJA. So let's look at these. We have BHA is right here, and we have CJA right here. They may look like they're the same size, but we are not shown or told that they are congruent. So just because something looks like they're the same size, and this even applies to not just angles, but also segments. Just because they look like they're the same length or that they are the same measure does not mean that we can assume that they are. We have to be told either in the given information or identified as such on the diagram. And finally, I cannot assume that line AD is perpendicular to line BF. Or I cannot assume that the measure of angle AHB is equal to 90 degrees. So when we look at this, here's line AD and here's line BF. They may look like that they're perpendicular, meaning that they intersect to form right angles. But if we're not told that it's forming right angles or that the angles themselves are right angles, by either told that they're equal to 90 degrees or shown on the diagram that it's a right angle, we cannot assume that it's a right angle or if they are perpendicular. Example 3 says, sketch a diagram showing that ray FH is perpendicular to segment EG at its midpoint M. So let's first just draw the ray and the segment. To start, I'll draw the ray FH. So the F was listed first, so it's the endpoint, and then H is somewhere else on it. Then I have segment EG, and I know it's supposed to be perpendicular to ray FH, so I'll draw it just like that. I know a segment has two endpoints, so I'll identify those. G down here. And I also know that ray FH is perpendicular to EG, so I'm going to put a little box right here showing that the ray and the segment are perpendicular, forming right angles. And I also know that they are intersecting at the segment's midpoint M. So this point right here is labeled M, and to show that it's midpoint, I will put a tick mark here and a tick mark here to show that EM is congruent to GM. Next, we have some more vocabulary. A line is perpendicular to a plane if and only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects it at that point. Notice that we use the if and only if here. Knowing that it's an if and only if statement means that this is technically a definition just written as a biconditional statement. Remember that from section 2.2? If you don't, I'd go back and look at my notes from that. So here again, a line is perpendicular to a plane if and only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects it at that point. You would identify that with the same little box that you would for two lines when they're perpendicular, showing that they're intersecting to form right angles. The next example will show you a diagram of a line perpendicular to a plane. So as stated on the previous slide, you can see here that this line is intersecting plane S, the horizontal plane, to form a right angle. So I would be able to say that this line, we'll call it line EB, or you could call it line EF, is perpendicular to plane S because it is intersecting to form a right angle right there. So example number 4 actually wants us to circle the statements that cannot be assumed from the diagram. So we're only going to circle the ones that cannot be assumed. So first we have points A, B, and C are collinear. So if we look at the diagram, points A, B, and C, they are all on the same line. They are not just free floating. We do see that they are all on the same line. So we can assume that points A, B, and C are collinear. Next, we have line EF is perpendicular to line L. So first, let's find line EF. Here's line EF, and it is perpendicular to line L because we know that it is forming a right angle right here. So we do know that line EF is perpendicular to line L. Next, we have line BC perpendicular to plane R. So line BC right here, perpendicular to plane R. We only know that line EF is perpendicular to plane S. We don't know that line BC is perpendicular to plane R. So we cannot assume that line BC is perpendicular to plane R. Next, we have line EF intersects line AC at B. Remember, we can assume where two lines intersect, but let's first look at the diagram. So line EF intersects line AC at point B. That is verified on the diagram, so we can assume that statement. Next, we have line L is perpendicular to line AB. So here's line L, perpendicular to line B. Again, we only know that this line, EF, is perpendicular to the plane and all the lines inside that plane. We do not know that line L is perpendicular to line AB, so we cannot assume that those two lines are perpendicular. And finally, we have points B, C, and X are collinear. So here's B, C, and X. So in this case, we aren't shown that B, C, and X are all on the same line. And we cannot assume that X would end up also on the same line as points B and C. Unlike when we had the first statement, A, B, and C, we saw that all of them actually do lie on that line. So we do know that they're collinear. But the fact that X is lying off the line, we cannot assume that if we extend the line in that direction of X, that X will actually end up on the line. So we cannot assume that points B, C, and X are collinear. That's it for this section. Make sure you write down any questions that you have and bring them to class the next day so that we can cover anything and move on. We'll see you then.